So hello everyone. So today we are going to start the new topic, that is process dynamics. This is fourth lecture of this module. So if you remember, in the last lecture we discussed the process control system. In that we discussed what is process control, what are the objectives of process control, and what are different types of process control. It is manual or automatic, whether it is a feed forward or feedback type, and what are the key components. So if you are talking of the process control, the key component is you need to have a measuring devices, you need to have a controller, you need to have a final control element, and of course there should be a process which need to be controlled. Going ahead, and today we are going to see, when we are going to do this process control, then what is process dynamics. Because when we are dealing with living system, everything changes with the time. So in order to respond for any disturbances, it takes time to reach to a new equilibrium. So there should be a dynamics, and today we are going to discuss the same process dynamics. So for that, one key parameter comes degree of freedom, which gives how many maximum number of variables that are required to define the system. Then we will be seeing couple of examples like CSTR and a simple chemical mixing process. Then finally we will conclude by this process dynamics and mathematical models, because when we are saying dynamics means we may deal with differential equation, it may be the ODE, it may be the partial differential equations, or it may be simple algebraic equations. As I told, process dynamics means how the process variables are changing. For example, let us say temperature, pH, dissolved oxygen, substrate and biomass with time. So when we are studying the same how process variable changes with time, then the process is called process dynamics. And particularly, as I told, in a bioreactor we are dealing with the living system, and living system is the dynamic. So entire parameter including temperature, pH, dissolved oxygen, even biomass, substrate and product, all are having dynamic profile. And then why it is important? By process control one can predict that and adjust the changes. What does it mean? It means for the process control, as I discussed, we need to monitor the controlled variable, that is outlet, and once you are measuring, then you should be able to make necessary changes for the desired aim or desired goal of the process. Now what are the basic elements here in the process dynamics? So it is basically cause and effect. Cause and effect. Cause means input may be your feed flow, it may be agitation, aeration, heating input, or even nutrient addition. Process is a bioprocessing in which mass and energy balance happen in a bioreactor. Output, what is output? You can have the biomass concentration, you can have product formation, even dissolved oxygen can be considered as output, pH, even carbon dioxide generation. So these can be considered as output. This is the cause and this is the effect. In addition, there comes disturbances, that are the unexpected changes. It may be the contamination, it may be power fluctuation, or it may be some manual error as well. So what is the rationale for dynamic models? So typically when we are saying it is changing, means we are talking unsteady state. So unsteady state models are also referred as dynamic model, and they play a central role in bioprocess control and can be used to improve understanding of the process, how it is progressing. It can use to train the plant operating personnels. It helps to develop a control strategy. It is very important for a new process, and optimize process operating condition. So, you want to optimize the process operating condition, you can test those conditions in a different setup. If it is working fine, you can then apply for the actual process. So, what it is saying, once you are having the process dynamics, you are having a model where you can train the personnel, you can improve the understanding even without having the physical process or the actual process. So, it is a kind of a mathematical model. Now, next question comes, what are the different type of model? So, one can be theoretical model, second can be empirical models, and third can be semi-empirical. Theoretical, they are developed using principle of chemistry, physics and biology. Empirical model, they are obtained from the by fitting certain models to the experimental data. They may not have this fundamental theory behind those expressions, but they are satisfying to the trained data or the given set of data. So, what it says, the theoretical model have a broader applicability, while the empirical model have a comparatively narrow range. Next comes semi-empirical. So, this is particularly a combination of models in category A and B. So, numerical value, let us say numerical value of one or more parameters in the theoretical models are obtained from the experimental data or the empirical models. So, what are the general modeling principles when we are going for the to model the process? First is you need to define the system boundaries. You need to identify the input, output and internal variables, and in addition, for these input, output and internal variable, if any range is there, that also we need to define. Then modeling approaches. Before going ahead, the first is to draw a schematic. You draw a schematic. Here you are having inlet, you may have the multiple inlet as well as multiple outlet, and label all process variables. Then select empirical or mechanistic model based on the data availability and physical law like mass and energy conservation laws. Then you need to perform a degree of freedom analysis that we will be discussing next to ensure that model equations can be solved. Then once you are having a details of model, the next is how to solve it. So, for that we go for the simplification and making certain assumptions, like simplify the model using assumptions like steady state, linearity of, we say that it is a perfectly mixed. To ensure computational feasibility, we simplify that it can be this computationally solved. Then next step is computer simulation and subsequent data analysis. And once it is done, then this is very important step, you need to validate the model. Validate the model by comparing the prediction to the actual behavior, and further you need to refine using feedback and new data. So, in this way we keep on upgrading the models. Now, we discuss if you want to have a solution, we need to understand what is degrees of freedom. So, it says degree of freedom indicates the number of independent variables that can be specified in a process system. So it means it says maximum number of variables that can be fixed. First it says maximum number of variables that one can fix. Or it says minimum number of variable which is required to define a system. Now how we calculate is a degree of freedom is difference between number of variables minus number of equations. So if number of variables and number of equations are same, we get 0. It means you are having the exact solution and system is fully specified. If degree of freedom is greater than 0, it means you are saying it is a underdetermined and it can have multiple solutions. And when degree of freedom is less than 0, it says it is a overdetermined, and in that case it is difficult to find a solution. Now what is its application in control design? So degree of freedom analysis helps design control strategy by revealing the variable flexibility in a process manipulation. So it will give the information how many equations are required, how many variables you can fix. For example, the output variables that will be obtained by solving the process model. So they are typically considered as a response, and input variable to be either, as I tell, it may be your disturbance or it can be your manipulated variable which you have monitored and you want to make necessary changes in the controlled variable through manipulated variables. So let us see one example here. You are having this stir tank blending system where two streams are coming, stream 1 and stream 2 are getting mixed, and this is the outlet. We are having two inlet and one outlet. Now first thing, we can simply apply this mass balance equation to write the unsteady state balance. So in the case of unsteady state, what is the inlet? X1 W1 plus X2 W2 minus what is outlet? X into W, and for time being if you are assuming there is no generation and there is no consumption, then this will be equal to the rate of utilization, that is defined as D rho V X upon dt. So this is the rate of accumulation, this is inlet and this is output. Now let us consider degree of freedom analysis for this system. So you have two parameters here, that is the volume and density. How many variables we have? X, X1, X2, we have X, X1, W1, W2. How many equations we have? Let us say we have one equation. So it says degree of freedom will be number of variables minus number of equations, so we got the 3. It means 3 number of variables that can be fixed. What we can specify, let us say we can say there are two disturbance variable parameter, that is x1 w1 and one manipulated variable parameter, that is w2. So we are having these 3 parameters, it is matching with the degree of freedom. If it is 3 means we can fix the 3 parameters, or we can say this 3 more parameters need to be specified to define the system. So in this way degree of freedom helps to understand what are the input variables that can be considered either manipulated variable or disturbance variable. So, why we are saying x1 w1 as a disturbance variable? Because there can be certain change in the inlet, and why we are saying w2 as a manipulated variable, because in order to set the value of x, we are going to modify the W2 flow rate in such a way that we can set the desired value of x. Now, we will see two cases here. First is a continuous stir tank reactor. So, it continuously operates. So, there is a continuous inlet and continuous outlet, and typically the feed rate remains or the flow rate remains same. Typically it operates at steady state. So, once we draw this flow diagram, so in the feed also we are going to have substrate, you are going to have the biomass, we may have a product, and in the product also we are going to have this, if it is Si, Xi, Pi, and this will be SO, XO and PO. The next step is to do the mass and to do this mass and energy balance, and once you do, then you will get the desired equation to see or to get the, you can say, the output or the response parameter. And as we have discussed in the previous lectures as well, CSTR have a wide range of application starting from pharmaceutical to wastewater treatment and petrochemical industries. Now, let us consider further that we are considering only a simple liquid phase in a CSTR, and irreversible chemical reaction is taking place. And so, A is getting converted to B in a CSTR. What will be the rate of reaction? Ra will be first order K into Ca. So, this is first order. One can consider the higher second order and so on and so forth. Now, if you do the same mass balance, what is the inlet? F into, let us say, Cai. What is outlet? F into Ca minus, there is no rate of generation, 0, minus rate of utilization is Ra into V. This will be equals to the rate of accumulation, that is the V into dCA upon dt. For time being, we are considering V as a constant. So, further we can write F Cai minus Ca. Ra we can replace as, considering this first order, K to Ca B, this equals to the V into dCA upon dt. So, what it says, you got some sort of differential equations, and depending on the system, this equation can be linear, it can be non-linear, and if it is non-linear model, so they need to be solved by numerical integration techniques. We cannot have the exact solution for those equations. So, let us see another simple example here. So, we are having a chemical mixing process. So, here the stream 1 and 2 are getting mixed to get stream 3, and then it is coming in a vessel which is having volume of 150 liter, and finally it is going to the reactor. So, first thing, there is a mixing tree here. So, here you need to do the mass balance. So, what is coming? Ca V1 is coming 10 liter per minute, V2 is coming 20 liter per minute, and then V3 become 30 liter per minute. So, 10 liter, 20 liter, and you sum them up, it becomes 30 liter per minute. Now, what is the concentration of A here? 1 gram, here 4 gram, and Ca3 we need to quickly find out. So, first after mixing, let us find what is the concentration which is going to this vessel. So, this will be Ca1 V1 plus Ca2 V2 equals Ca3 V3. So, this is 1 into 10 plus Ca2 4 into 20 equals, this becomes 90 divided by 30, this becomes Ca3. So, we are going to get Ca3 as 3 gram per liter, that is going to this vessel and followed by it is entering to the bioreactor. Now, there can be certain disturbance. So, assume the disturbance as the operator switches the flow rate by mistake. So, now stream 1 has become 20 liter and stream 2 he opened the 10 liter per minute. So, what he did, stream 1 he opened 20 liter per minute and stream 2 he opened 10 liter per minute. Now, what will be the Ca3? Ca3 will be now, if I do the same calculation, so this will be 20 into 1 plus 10 into 4 divided by 30, this will be Ca3 and this is coming out to be 40, 20, it comes 2 gram per liter. Now, all of a sudden what happened, this there is sudden decrease of Ca3 value from 3 to 2. Now, here comes the dynamics, because when there is change it will take certain time to see these changes, and finally this Ca at a steady state, when if it was 3, then it also has to gradually come down to 2 gram per liter. So, now you just consider this 30 liter per minute was entering here, and what happened, the concentration of A it gradually dropped from 3 gram to per liter to 2 gram per liter, and accordingly the response Ca also this need to change from 3 to 2. So, what does it mean? It means a new steady state need to be established. So, just to see that how long it will take to reach the process, we can do this mass balance here. So, what in the mixing vessel, what is entering there, inlet is V3 into Ca3, what is outlet, V3 into Ca, what is the rate of accumulation? Rate of accumulation is V into dCA upon dt. What is the volume is 150 liter. So, if you solve this equation, you should be able to see the how the Ca will reach to the new steady state value. So, it says V into dCA upon dt equals V3 into Ca3 minus V3 into Ca. Now, V3 value we know, this is 30 and this is 150 liters. So, if you divide, you will get the 5 into dCA upon dt plus this equals inlet is, let us say Ca3 minus Ca. Now, you can rearrange here. So, the Ca3 we already know this is 2 and Ca we need to find how its profile is changing with time. So, you can write 5 dCA upon dt plus Ca equals 2. Now, we can quickly differentiate it to get the solution. So, it will be dCA upon 2 minus Ca, it will be dCA upon 2 minus Ca, you can integrate, this will be 1 by 5 integration of dt. So, here it will start from 0 to 2 and this will start from 3 and it will reach to the a value of Ca. What is the initial value of Ca? Ca naught was 3 gram per liter. So, now it is gradually decreasing from 3 to 2, and you will just see how it, which profile it will follow. So, this is simple ln 2 minus Ca if you apply the boundary condition here. So, final equation will be Ca is changing as Ca is 2 plus e to the power minus t upon 5. So, what it says, with the time this will decrease or reach to the new value from 3 to 2. In this way we see this is the dynamics of this process. So, because of the disturbance it is reaching to the new steady state value. Now, after understanding this, what we have discussed so far is what is the process dynamics and mathematical models. So, dynamic behavior or the process dynamics includes transient response, it may be after disturbance and reaching to a new steady state behavior at equilibrium. So, typically what do we mean by transient means it is a short term response to changes, and steady state means it is a long term equilibrium condition. So, time between these two we need, if you want to understand, then we need to see what is the process dynamics, what are those mathematical equations which will define the changes. Then next comes the mathematical modeling. So, they can be differential equation, model parameters and rate of change. It may be first order or second order systems, or it may be a linear or non-linear models. The transient response of the outright variable as a function of times are calculated by the numerical integration after specifying the initial conditions, input and time interval at which the system to be integrated. As we did that, what is the initial and final time, what is the initial and final condition, and what is the input. Then if it is a nonlinear equations or it is a kind of a ODE or PDE, then there are large number of numerical integration techniques are available. For example, Euler method or Runge-Kutta method. In addition, nowadays there are popular software packages are also there to solve those mathematical equations like MATLAB, Mathematica, Polymath, LabVIEW, MathCAD and so on. So, what we discussed today is whenever there is a change in the process, and particularly bioprocess, we are dealing with the living systems. So, the process dynamics need to be understood, and for that you need to develop a mathematical models, and after that you need to explore different way to get the solution for the same. Then only with time we should be able to define how the particular process variable is, or those variables are changing with time. So, with this I will stop here. Thank you so much.